Okay, recording started. And I'll go back to the screen share to show you what we're going to do today. Let's see. Here we go. And yes, to go over what we're going to do today, you can see just like yesterday, we have a link to the full text version of the lesson as well as the slides version of the lesson that we're going to go over. And I also wanted to point out one thing about the full text version of the lesson that I didn't mention yesterday is that all the lessons have sort of exercise problems at the very bottom. That if you want to do more, you can try out those, and I have answers to them as well. So that's just something you can take a look at if you are interested. That was pretty much the logistics. And I'll just jump into the content now and start talking to you about the next exciting step on our journey of learning how to be Bayesians. But first, we'll just briefly review what we talked about yesterday. And again, this is sort of lesson 3, going all the way back to last year when we did lesson 1. And the same deal. We're going to have a worksheet today. Again, a new one. We're going to start a new one from yesterday. And so far, these are the topics that we've covered, which hopefully some of these terms will start to look familiar to you now. We've talked about how the prior and likelihood combine to form the posterior distribution. And at least in what we're doing here, we figure out what the posterior distribution is by sampling from it with the Monte Carlo method to approximate that distribution. And the posterior is what we use to actually make inferences. Like that's what we make our predictions out of. That's what we use for hypothesis testing. It's all about the posterior. And so that's what we've mostly been working with. And we've done a bunch of different types of models going all the way up to generalized linear mixed models. And we've looked at different response distributions. We've done normal, we've done binomial, and we've done gamma, and we've done various types of random effects as well. And today we're going to add another component to our sort of toolkit when it comes to mixed models. And we're going to look at how to deal with situations where we have correlation in space and or time. And so some people know that as repeated measures. And we're going to do that both by looking at residual correlation structures and additive models. We're going to have an example of both. And we're going to do space and time. So you should be excited. You're going to learn a lot of powerful new skills today. So today it's going to be all about space and time. And the basic idea behind this and why do we have to care about where things are located in space and time is, well, some people call it in geosciences, it's called the first law of geography. The closer two things are in space, the more closely related they are. And the same goes for time. The closer two things, whatever they are in the world, are in time, they're going to be influenced by the same causes, are going to be working on them, and they will tend to be more closely related. And that will show up in the statistics as well. You'll have a higher correlation between measurements that are taken near each other in space or time versus ones that are far apart. All else being equal, that's a pretty decent assumption to start off of. And so, yeah, I put this picture of like the space-time continuum. Even though we're not physicists, we can kind of think of space and time as similar in terms of statistics, because the statistical model doesn't care whether it's space or time. It's modeling things closer together on whatever axis that is as being more correlated. So it's like space and time are just different dimensions of the same thing for our purposes as statisticians. So one example let's say we wanted to do a study on how different management treatments of farms affect soil carbon sequestration. I know a lot of folks on ARS are working on just that. And well, we might want to obviously replicate our observations or our manipulations on many farms to make a general broader inference about how these management practices work on all farms. We want to have replication and randomization because that's how studies should be designed. Well, you might put these farms, locate the farms for your study in some geographic area. Some are going to be closer to each other than others, right? And the closer together two farms are, the more likely they are to have similar environmental conditions, similar soils, similar climate, similar cultural practices or whatever. They're all going to, we can assume the closer they are in space, the more similar. And that means that even if those farms are independently assigned to different treatments, or even if they independently decide how to manage their land, they're not statistically independent. Some of the variation in their response of soil carbon or whatever you're measuring is going to be correlated because of the same soil type, the same climate, and so forth. And now you might say, well, that's more of an issue with an observational study because we can't control over all those variables, in the real world. Well, we have designed experiments. We don't have to worry about that stuff. Well, yes and no. You still have to worry about it a little bit because design experiments take place in space and time, and some of your experimental units are going to be closer in space and time than others, and they're going to be more correlated. So it's something you have to worry about no matter if it's an observation or an experiment. So I just wanted to make that point. Well, this means that we're going to have to make a switch in our thinking of everything we've done so far, at least slightly. We have so far, all the models we've done so far have had residuals. Residuals are like the error or the variation in the data that's left over after everything that can be explained by the model. And so far, every model that we have done in this course have assumed that any one data point's residual is independent of any other. If what we do yesterday, we did like the turnip yield plots. So it's like as after you've accounted for all the fixed effects, the treatment, after you've accounted for what block that plot is in, we've accounted for those fixed and random effects, then any variation in a particular data point is just random. It has nothing to do with any of the other data points. That's what we've assumed. And yeah, whether it's fixed or random. And yeah, so all the random effects we have put in have been sort of block level. People that use SAS may know the term G-side random effect. I never heard that term outside of SAS, but in SAS they call it G-side random effects because basically the G matrix is the variance and covariance of the random intercepts and slopes in the model is called G. So if you have random effects like we have done, random intercepts and slopes, they're called G-side random effect because they're in the G matrix. Anyway, that may mean nothing to you if you don't use SAS, but so those are the kind of random effects we've done. They still assume that after you've accounted for everything, all the residuals are independent. Well, that's a decent assumption in many cases, but if you have correlation or variation in space and time in your data, that can make that assumption invalid. It's no longer the case that the residuals are completely independent after accounting for all the fixed and random effects if you still have some pattern in space or time where things that are closer together are more closely related. They're not varying randomly independent of each other. They're correlated. So we can't make that assumption anymore. It will give us bad results. Well, how do we address this issue? We've now determined it may be a problem. What do we do about it? Well, there are two ways to deal with that. And we'll talk about one within the framework of a generalized linear mixed model. We can say, okay, yes, the residuals are correlated. They have a covariance. Let's model that with some covariance parameters in the model. And so we can actually put a number on it, a parameter for how closely correlated some data points errors are based on how far apart they are in space and time. And if you know SAS lingo, you might have heard that be called R-side models or R-side random effects, because the matrix, the covariance matrix of residuals is called R in some statistical notation. So they call it R-side. So yeah, basically we said, okay, residuals have a pattern in space and time. Let's throw some numbers on that in our model and estimate parameter for how correlated they are, and that'll give us a better result, better answer overall, because we're accounting for this unwanted variation in space and time that we have to address before we look at what's really going on with our treatments or whatever thing we care about. Any questions so far on that? This is a lot conceptually, so if anyone has a question, please ask away. And there's a second way, besides putting all the space and time variation in the residuals, we can actually put it in the model as a basically covariate in the model. And oftentimes the way that is done, I see we have a question, so I can't see the chat. Can you just read off the question? Or actually, I can put it up here.
Yeah.
Here we go. Yes. Do we test that residual correlation question, or are you jumping into dealing with it? Yes, I will show you how to diagnose and test the issue with residual correlation, as well as deal with it. Yes, so we're gonna do that for sure. Thank you. Yeah, so yeah, the two main ways to deal with it is, number one, as I just said, put it in the residual covariance structure, or number two, you can actually just model the space and time effect directly. A lot of times those effects are not linear, so we have to use a additive term, a spline. Some call it a smoother, some call it a spline. It's basically a wiggly, nonlinear function of space and time that you can just put in the model. And then we kind of have left strictly the world of GLMMs, and now we're in the world of GAMs, generalized additive mixed models. I'll get back to that because that's sort of part two of today. I'll get back to that, but I just wanted to introduce you to both ideas. We'll do that again for the second half of today. So we're going to do two examples today, one of each of the things I just mentioned. We're going to, number one, do a generalized linear mixed model to look at, and we're going to put the time covariance in the residuals structure of that model. And then we're going to do a GAM additive model to model the relationship in space. You don't have, you could switch around. You could do a residual covariance for space. You could do an additive model for time. You could even do them both in the same model. These are just the example. Yeah, so you could do a GAM that's over time, not space, and vice versa. These are just the examples we're going to happen to do today. But you could do any of these solutions would work for space and or time or both. So yes, that is the intro kind of for today. And so now we're going to just hit the ground running with an example data set. But I'll continue to add a bit of background as we go, doing our residual covariance for repeated measures in time. So people probably heard the term repeated measures a lot. That's a situation where you can have time dependence. If you repeatedly measure the same subject, the same experimental unit at different time points, whether it is a plot and a organism, animal, whatever it is, you've measured it at different time points. Well, if you take measurements from the same unit, the same plot, the same individual at different times, they're not independent. You know, if you're measuring growth over time, maybe one of them started out bigger and one started out a bit smaller. So if you take multiple measurements from the same individual, those are not independent measurements of body mass or whatever, they're correlated because they're from the same individual on different days or whatever. So we have to account for that. And yes, so we're going to get into our posit cloud, or run it on your own machine again. And I'll go in there and get everything going. But I just want to mention first, what I would like everyone to do is to restart their R session on Posit Cloud to just have everything clean. I'll show you how to do that. And then we're just going to load all the packages again, just to make sure there's nothing cluttering up your workspace. And we were loading all the same packages from yesterday, except the same plotting options and model fitting options. But we're going to use this ape package as well a bit today, and that's what we're going to use, Amanda, to test formally for spatial autocorrelation in the residuals. It has some function that can do that. Let's see. So I'm going to go back into Posit Cloud and open up my project, same one from yesterday. So let's go ahead and do that. And it will take a minute to, let's see. So we have a question. Can we tune parameters by modifying initial residuals to get an accurate result? Yeah, basically I'll show you a bit of this. There are different ways to model the residual covariance structure, and often people do take kind of a data-driven approach and try out different ones and see which one is the best fit. And that's what we're going to do in this case as well. So I think that's what you're asking. So yeah, so I'm back in my Posit Cloud. I'm going to close my worksheet from yesterday. I'm going to go ahead and click on this broom icon up here in the environment pane, and that will clear out the workspace from yesterday, as we're not going to mess with it anymore. And then I'm also just going to go ahead and go to session and restart R up in the top menu. That is just to start with a clean slate. And hopefully, yes, it should reset the command stand path, so it will find that. Now let's open up in the files pane the lesson 3 worksheet. I'll just clear this console log as well using this little broom just to make everything look nice and clean. And you don't have to do that, but here we go. So I have the lesson 3 worksheet open, and I'm going to run the setup stuff. Control Enter, everything up to line 30. I'll run, and that will load everything. Okay. So we're all good to go there. And going back to the slides, we're going to talk about the example data that we are going to work with. And once again, I'm glad the AgriDat package exists because it has nice, clean little example data sets that we can work with. Obviously, these are much cleaner data sets than things you'll obviously in real life. A lot of the work is just getting the data into this format, but that's not really the point of this workshop. So we're working with some nice, clean example data sets that are already all nice and neat. Actually, there are some missing values in this data set, but I believe from individuals that died, but we are going to just ignore that issue for today and just not worry about it because it's only 1 or 2 missing values. So this data set is called Diggle Cow, and it is dealing with bovine tuberculosis. Here's a picture of a cow that's not doing so hot. They're infected with tuberculosis. And they were trying to look at whether iron supplementation could be used to mitigate the negative effects of tuberculosis on weight gain. So the cows that had tuberculosis did not gain weight as well, and they wanted to see if they could help that by giving iron to the animals. And so we have 26 cows, and each cow has a numerical ID because their weight is measured at multiple time points. So we can track the same cow was measured at different days. And they, I don't know if they randomly infected cows with tuberculosis or if they just had some that were infected and some that weren't. But some of them are infected with tuberculosis and some are not. And out of those two groups, they also had in each one, some were given iron and some were not. So it's 2 by 2. 26 individuals split among 4 treatment combinations. So there's like 7 or 8 individuals per treatment combination. And they measured their weight on 23 different days, roughly evenly spaced in time. And we're going to load this data set. And then I always like to, this is not really necessary, but it's a nice thing I like to do. If you have a logical control group in your treatments, I always like to set it so that that is the intercept level in a statistical model. So it's the opposite in SAS, but in R, the first level in the factor ordering is the intercept, the reference level. It makes sense for the control group to be the reference level, because then if no iron is the intercept, and then the coefficient will be the effect of iron relative to the control. So let's load the data set, data, diggle.cal. We'll run that line, control enter. And then we'll fill in the blanks here. Both cases, we're going to use the relevel function to change the level of the factors. And ref equals is what we said is the reference or intercept level. Relevel and ref. Control enter. And you can see, I'll just show in the environment tab the different columns. There's only 5. Yeah, the animal ID, iron. Basically, it's like a bunch of 1s and 2s in there. 1 is the reference level, no iron, and 2 means iron. Same thing with infect. This is their weight, I assume in kilograms, and the day on which it was measured, calendar day. Now, before we do any stat modeling, we're going to plot the data. And the way I'm going to do that is I want to plot every animal time series of weight as a line colored in by treatment combination. And also just so we can kind of get a general idea of the difference in the treatments, I'm also going to use this stat summary line. So for each combination of iron and infection, so each of the 4 treatment combinations, I'm going to plot the median at each day as a thicker line. Line width equals 2 to make it thicker, and then we can see we can both see the individual variation and kind of summary in the same plot. So let's see. We'll have. Let me see. What did I want to do? Yes, day is the x-axis, weight is the y-axis. We're going to do iron as the color, and then we're going to have solid and dotted lines for the infection. So we'll have 2 different colors and 2 different line styles on there. And then animal is the group. So that means a separate line will be drawn for each animal. So that's how you do that. So we want day for x-axis. Yeah, so ggplot always is very explicit about which column in the data is going to which element of the plot. X-axis for day, y-axis for weight. The iron column is being used to tell you what color the lines will be. And the infect column is what style of line. And then the animal, each cow is a group. So let's draw that plot. And you can see we get a warning about a missing value. That's, I believe, because of one individual that died or otherwise left the study. And so it has an NA, a missing value in there. Again, if we had a lot of those, we would probably want to incorporate that into the model somehow. But since it's only one data point out of 600, I decided, at least for the purpose of this example, we're not going to worry about it. So what do we see here? We can see the cows are kind of gaining weight over time. they're sort of like, it's not quite linear. They kind of, you see that it, as often you see with weight gain trends, it starts at a higher growth rate and then kind of starts to level off because cows can only get so big. But it's close enough to linear that for this purpose, we're going to model it as linear. And you can also see, okay, the dotted lines, the infected cows are doing more poorly than the cows that are not infected. Obviously, the dotted medians are lower than the solid. And there's maybe, the no iron actually is, the medians are a bit higher than the ones with iron, orange versus blue. But it's not a huge difference. Another thing to possibly note is we have also a bit of a relationship between the mean and the variance. When the cows don't weigh as much, it's all closer together. Over time, it spreads more. So there's kind of, as it goes up, they vary more. Now, I think we're kind of just going to ignore that small wrinkle for the purpose of this example, but that would be an improvement that could be made to deal with by either transforming or assuming non-normal residuals. But we're going to, since I can only kind of hit you with one thing at a time, we're just going to work on the time dependence aspect of it right now. And what I want, another thing that we're going to do to the data before we stick it in our Bayesian model is we're going to scale the variables. Now, anytime you take a variable and either just multiply it by a constant or add or subtract a constant from it, that doesn't really affect the distribution of that variable at all, right? It's the same exact distribution. We've either just moved it up and down, or we've multiplied it to or divided it by a number. But so why do you even bother with that? Well, large or small numerical values, when it comes to Monte Carlo sampling, it can cause numerical issues. So it is often a good idea to transform. You're not really transforming, you're just scaling the variables so that they are all kind of in similar units, like around, not going up to millions or 0.000001, but it's like 1 to 10 kind of order of magnitude, all about the same. That helps a lot with the sampling. And it also, another very useful reason to do that is because it helps a lot with the priors. If you scale your variable so it's in standard deviation units, you can always think of the same prior distribution of the fixed effect also in standard deviation units. You don't have to be like, well, this parameter is units in milligrams and goes up to thousands, so I want the prior to be normal with mean of 0 and standard deviation of 100. This one is like only in smaller units, so the prior is mean of 0, standard deviation of 1, or whatever. If you scale everything to be in standard deviation units, you can use the same priors for all the fixed effects without having to think about units on them. So that, and it won't affect the inference because you're just multiplying and adding by constants, so it doesn't affect the inference. So I always do that. Well, we're going to do the day column begins with 100 something, so I'm going to subtract off the minimum so that the day column begins with 0. So just days since the start of experiment. For some reason, it doesn't start at day 0. I guess it's starting from the cows were 100 days old or something when the experiment started. So I'm just going to subtract off the minimum there. And then I'm going to use the scale function to z-transform or standardize the weight variable, which means we are going to rescale it so that the mean is 0 and the standard deviation is 1, so that everything is in standard deviation units. And so someone says, for very large or very small units, yeah, thanks, Anna, is that in absolute values or relative to the data distribution? Do you mean, can you clarify what you're asking?
Well, so, you said roughly values of 1 to 10 are manageable. What if just the scale of the data you're using are on hundreds of
Yes.
thousands?
Sure. So if a variable spans many orders of magnitude, then it will be probably then there you can't scale it all to be in the same order of magnitude, obviously, but that is a variable like that can be problematic for model fitting anyway. So it's like, well, maybe you could take the logarithm of it and then
So it's more just about
Yeah.
being on the same order of magnitude.
yes, that's right. As long as everything, all the predictors, if they're continuous, are scaled to be on a similar, you don't really have to, but it's like a good practice. Yeah, it can help. So let's do this transformation and on day and weight. Yeah, you can see the x-axis on day starts at 100 and something. So we're gonna say make a new column called day after start by taking day and subtracting off the minimum of that column from it, min being the minimum. And weight, we're going to make a new column called weight scaled, weight underscore scaled, by calling the scale function on the weight column of the original data. So now instead of having 5 columns, we're going to end up with 7. So I'm going to run both these lines, highlight them, and hit Control Enter to run them. Now you can see we got 7 variables. Days after start, it goes down to 0, and weight scaled, everything is like in standard deviation units away from the overall mean of weight. Yes, and James, we can untransform that when it comes to the results. You would then take, yes, I'll show you how to do that. You just have to go back and add back on the mean and multiply by the standard deviation again, because what you do to Z transform is subtract the mean and then divide by the standard deviation. So so we multiply and then add it back on. And now we're going to fit a statistical model to this data. Is Z transformation the same thing as Z scores? Yes. A Z score is the Z transformed, a variable in standard deviation units, because the Z refers to the standard normal distribution, the normal distribution with mean of 0 and standard deviation of 1. Are there cases where I would want to subtract the median instead of the mean? Yeah, you could also scale it by the median as well if you wanted to. The median is more robust to outliers. But yeah, it doesn't really matter too much for this purpose because, again, it doesn't affect the distribution of the data if you subtract a constant from it. So if you subtract the median or the mean, it's not going to make any difference for the model. It's just like whatever one you'd rather do, because they'll hopefully, if it's symmetrical, they'll be similar anyway. So whatever, it's just a practical question of whatever works best. So now we're going to fit a statistical model. We want to know if the weight gain over time is affected by the combination of the treatments. So that means weight, we're going to use this scaled weight variable as our response. And not only are our 2 treatments going to be in the fixed effects, but also time is a fixed effect. The days after start is a fixed effect as well, because we actually want to know it's not a random effect, it's a fixed effect, because we want to know whether the slope of the weight versus time line is changing as a result of the treatments. So we want to know, we're actually comparing time as part of this model. So we want time to be a fixed effect. So there's these ones, iron and infect, are categorical variables, and days after start is a continuous variable. And we are going to use asterisks to show we want all possible interactions between the treatments and interactions between treatment and time. All possible interactions up to third order. And our question that I just mentioned, the research question, is how is that slope, the rate of weight gain over time, affected by tuberculosis infection, and does adding iron to the diet help deal with that? Or does it harm? And each of the, but here's the thing, that's going to get you most of the way there. But what about the non-independence of measurements within individual cows? Each cow has her own unique time trend, and our model needs to account for that. The measurement of the same cow on different days is not independent. A question from Mahesh. I wonder if we are predicting the response variable as a product of the independent variable or simple regression with a plus sign. Yes, so if you would put plus signs instead of asterisks, it would not model the interaction. It would not model the interaction. It would only model the effective time and the effective treatment. It would force, it would, yeah, if you go back to the graph, yeah, these, if you didn't have an interaction, the model could not detect if the slopes of these lines are different. It would say, okay, we have time as an effect, so there's a slope, and treatment might move those lines up or down, but it can't, if you don't involve an interaction in the model, you couldn't test whether the slopes are different. So we have to have that interaction to test that. Okay, so now we're going to get away from the code for a minute and go back to a bit more statistics so we can understand how are we going to put this residual covariance into the model. Well, I said this already, but I'll say it again. Every model we've done up to this point has assumed the residuals are what's called conditionally independent. I mean, independent means they are random with respect to each other, and conditionally means after we've accounted for everything we can in the model, all the fixed and random effects, they're independent. But every stat model still has a residual variance and covariance matrix in it. All these linear models have one. It's called R. But if you look at it, basically all the models we've had so far have had 0 everywhere in this matrix except for the diagonal. Basically, these we have a variance sigma squared. That's like the variance of the residuals. And so we're saying, okay, the residuals have a variance, right? There is error in the data, but no two residuals are related to each other in any way. They're all random. So the diagonal is 1s, but everything off that diagonal is 0s. So every model we've done so far has had 0 everywhere in this R matrix except for the diagonal. The way we start to model residual covariance is by putting numbers that are not 0 into these slots. Then we can model them as being correlated. And this matrix for our time series model is going to be n by n matrix, where n is the number of time points. So this is just an example if there was 4, but our cow model has 23 time points. It'd be a 23 by 23 matrix. So there's more than one way to put numbers in here besides zeros. There's many ways to do it, but there's a few basic choices that seem to work well in practice, and so you usually choose between them. And there's a lot of ways. These are sort of the simplest ways. We're going to look at 3 options. One is called unstructured covariance matrix, one is called compound symmetry, and one is first order autoregressive. So that's a lot of jargon. What does each of those mean? Well, unstructured covariance is, in a way, the simplest, but it also has the most parameters. We basically just estimate a parameter for every single value off the diagonal of that matrix. So we have the matrix is symmetrical, so the correlation between 1 and 2 and 2 and 1 is the same. So we have, in the case of having 4 time points, we would have to estimate 6 parameters of covariance. The correlation between time point 1 and time point 2, the correlation between 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. We'd have to do 6, right? If n equals 4 time points. But obviously, the more time points, you're going to go up to a crazy number of parameters by the time you get to a lot of time points. So this is the most flexible model. Obviously, it could you could model any possible correlation structure with this because you're giving a separate parameter for every possible pair of time points. But it's hard to estimate that much parameters off a small data set, and you can easily overfit to the data if you have too complex of a model. So usually this is too much for our purposes, but I'm just showing it to you as a proof of concept for the most part. I wouldn't normally use this in real life. So how can we simplify? It's like, we don't want them all to be zero, but we also don't want every one to be different because that's too many. So where can we strike a balance? Well, compound symmetry is kind of a very simple way to do that. We just say, okay, we'll just estimate one parameter. They call it rho usually for all these, for all the pairs of time points. So that means any two residuals from the same individual are correlated by the same correlation coefficient, no matter how far apart in time they are. The correlation between time point 1 and time point 2 is rho. Same as this correlation between time point 2 and time point 4 is also rho. They're all one parameter. That's called compound symmetry. Same, just one non-zero covariance parameter. That's it. Now you can be like, well, that's maybe too inflexible, right? Like the correlation between two measurements that are 1 day apart should be higher than ones that are 100 days apart, right? I mean, this maybe is too inflexible. There's another idea. Again, these are just some of the ways you could do it, but these are the three we're going to look at today. First order autoregressive, some people call it AR1, is another way you can do this. And this models the correlation between two time points within the same individual is higher the closer in time they are, because we still only estimate one parameter, rho, but if two time points are 1 unit apart, their correlation is rho. If they're 2 time points apart, like time 1 and time 2 are 1 time unit apart, time 1 and time 3 are 2 time units apart, they're correlated by rho squared. Since rho is between 0 and 1, if you square it, it gets closer to 0, and eventually, if you raised a decimal number like that to a high enough power, it would pretty much be 0. So it means the correlation between two time points is high if they're 1 day apart, basically, and then goes down to 0 the further apart in time they get. First order autoregressive is the jargon for that. So again, it doesn't have any more parameters than compound symmetry. It just has one covariance parameter, but it allows the correlation to go down the further apart in time the time points are. So let's go over that again. Having no covariance and independent residuals, you're going to have zeros in this matrix, the covariance matrix. You could do unstructured and estimate a separate parameter for every one. You could do compound symmetry and estimate one parameter that's the same for every pair of time points. Or you could do first order autoregressive and estimate one parameter, but allow it to go, the correlation to go down over as two time points get further and further apart. And this also works for space. Same would work. You can do AR1 in space, and it would just be going further apart in space, then the correlation would go down. All this stuff works for space as well as time that I just mentioned. Any questions? So how do we determine the covariance structure? Well, I'm going to show you how to fit the different covariance structures to the same data and then do a model comparison to see which one is the best fit. So we're kind of just going to use a data-driven. Yeah, there's kind of two ways. You can either have a prior idea of which one will be most appropriate and focus on that, or you can do a data-driven way and fit the different ones and compare them. Now, I would say first order autoregressive is good for things where you're measuring like the weight gain over time, because we know that a cow's weight on 1 week is dependent on the weight a week before. But if you're doing something where there's like environmental fluctuations, like let's say you're looking at yield of a crop in the same plot over several years that has different climate in each year. It doesn't really like go up step by step. It varies up and down kind of randomly based on the environment, the climate. There might be some time dependence, but it's going to be more random. So they're like maybe the compound symmetry is going to be better because it's not the correlation between 1 year apart and 2 years apart and 3 years apart is not going to be that go down that much as it would for something like weight gain over time. So it's like partly you decide based on your knowledge of the system, and partly we can fit the different models and see which one just works best. So that's what, in this case, we're going to try out different ones and see what works best. Because we're pretending we're ignorant and don't know anything about cows or whatever. So we're just looking at this as just pure data that we're just trying to figure out what model fits it best. And yes, as I said, we're going to try them out all three as proof of concept, although I wouldn't necessarily, especially unstructured covariance, I would not try to mess with that if I was doing this in real life because, right, this matrix isn't too bad if you have the matrix, the unstructured one, isn't too bad if you've only got 4 time points. It's got 6 parameters, but we've got 23 time points. So there's actually, 23, choose 2, there's 253 parameters that you have to estimate. That's way lot for our data, which only has 600 data points. It's most likely that's kind of over parameterized, and you're going to have a lot of issues with model fitting if you try to fit that complex of a model to small data. Even Bayesian priors help, but it's not perfect. They can only do so much. So we're going to have an issue there. But it's like, well, but I'm going to show you it anyway, just as a proof of concept. And then we're going to do the autoregressive and the compound symmetry too. Okay, here is the syntax for the residual covariance structures. I put name here, but each of the covariance structures has a function that goes with it. The unstructured is called unstr. That's the function for unstructured covariance. Compound symmetry is called COSY, which is kind of cute, COSY, and autoregressive is AR. So that instead of name, you would write in the proper covariance function structure, and you have to specify which column in the data is the time variable, and GR is what is the subject, what is the grouping variable. So in this case, time is going to be the days since start. That's the variable that indicates time, and group is going to be the individual animal. That is within what are they correlated? It's within each cow they're correlated. So that's where it is called animal in the data. So we're going to use animal for the grouping variable. So yeah, so this is how it would look. Unstr for unstructured. In each case, it says time equals day after start and group equals animal. That's the same for all these. This function, the name of the function is different. Unstr, COSY, and AR. The only AR has a special argument, P equals 1. I said we're doing first order autoregressive. So P equals 1 indicates first order. You can model more complicated autoregressive structures with more complicated time lags between time points by going up in order, but we're not going to mess with that right now. We're just going to do a simple first order autoregressive. So P equals 1. Other than that, the only difference between these three is the name of the function, right? Okay, this is a bit technical, but I'll show you the models. I've fit 3 of them. You can see in each case, the model formula is almost the same, except for the covariance part is different. Here's the unstructured, here's the COSY, and here's the autoregressive. But I had to add a special prior to the covariance matrix in the unstructured because the model would not converge unless I set a very strict prior on that. And that is usually, Anna was asking about this yesterday, why doesn't the model converge sometimes, or what do you do? if you're trying to fit an overly complicated model to a data set, it will oftentimes have trouble converging. It can't find an answer because you're asking too much of the data, basically. So it's kind of a red flag. But as I said, I would not usually use this unstructured covariance. I'm just trying to show you it as a proof of concept. Again, where it's estimating way too many parameters. I had to increase the number of iterations as well to get convergence, which we also mentioned as a way to help with convergence. And I had to initialize all the parameters to 0 as well. For some reason, I needed to do that. So yeah, not recommended in practice to do. But in all the models, I've also put this prior of normal 0, standard deviation of 5 on the fixed effects. And that is a uninformative prior because we have, again, the mean is 0. So we're saying it's 50-50, whether it's a positive or negative effect. And the standard deviation of 5 because I've scaled weight to be in standard deviation units. So, and a coefficient of 5 would mean iron supplementation increases weight by 5 standard deviations, which is like a ridiculous amount. So it's a very wide prior. It's allowing for very large effect sizes. We're not biasing it a priori to small effect sizes. And yes, and by the way, I'll mention, I keep telling you that Bayesian is better than classical statistics. Because you can get answers in some cases where you can't with classical statistics. Well, this is one. I actually tried fitting all these models with a not Bayesian generalized linear mixed model package, and it didn't converge at all. I could not get, especially the unstructured covariance. There's no way you could get a model like that to converge in classical statistics because it's got way too many parameters. The Bayesian one, it took a little tinkering, but I could get it to converge if I used the right priors, which you could not do. Basically, you would not even be able to fit an unstructured covariance in classical statistics to compare it with the other models. It would not even converge. You couldn't get an answer. So we're starting to get into the territory where the Bayesian models actually work and the other options fail. So that's just a side note. So I'll kind of stop talking and actually run this code here. But it went to sleep because I was talking for too long. And just a second here. We'll do a little bit more, and then we'll take a break at 10 o'clock, I would say, since we've been talking for a long time. So yeah, so we want here's the unstructured covariance model. Our fixed effects are the iron treatment times infection status times days after start. Those are our fixed effects. They're going to be the same every time. So I'm going to fill that in there. Day after start. And we want unstructured covariance, UNSTR. Time variable is also day after start. And the grouping variable is animal. That's the name of the column with the animal ID in it. And I've left also the normal, yes, the set command stand path. Yep, let me do that. Yes, that if your thing fell asleep, it might reset that. Where did it go? Yes, I'll have to, oh shoot, it's not in the console anymore. Just a second. Should be, I'll put this in the chat in just a second. Oh, yep. Thanks, Bob, for doing that. Do that as well. There we go. So yeah, copy and paste that. If your thing fell asleep, you'll also need to do that. Okay, so now for the prior, as I said, the distribution is going to be normal. And for the fixed effects, class equals B is for the fixed effects. And you can see here, here's a prior on the covariance matrix over time, which doesn't allow the covariance parameters to get too big. It maintains them at small values. That's what that prior is doing. So we're going to run that one unstructured. It gives us a warning dealing once again with the 1 or 2 missing values in the data, but we're just ignoring them for right now. The compound symmetry model, it's very similar. We have the same fixed effects, iron, infect, and day after start. Same fixed effects. Only difference is COSY is the COSY, compound symmetry is the covariance structure. We have the same time as days after start, and GR for group equals animal. It's got the same prior. I didn't put a prior on the covariance matrix here because it didn't really need one. Again, because it's only got one parameter, it's trying to estimate, not 253. So it didn't have as much trouble. A much simpler model. And lastly, the autoregressive. We're going to put same fixed effects. AR is the covariance structure, and we have to add P equals 1 to specify its first order. Again, same normally distributed prior on the fixed effects, because all the models are the same fixed effects. So, okay, we've run all the models. Again, if you're doing this, yes, Mahesh, if you can run the line of code that's just above in the chat, that will reset the command stand path. Yes, it'll do that, and then it won't give you an error. Now we're going to look at the posterior predictive check plots, the model check, where we look at the distribution of the data and what the model is predicting to see if it's a good fit. PP_check on the unstructured covariance. Let's take a look. And so that'll take a second and then pop up a plot. So actually, this looks quite decent in the unstructured covariance. You see there's kind of a slightly bimodal distribution in the data, and the model, the blue lines, are picking that up. We have a good fit even with the unstructured. What about compound symmetry? I would say also similar. Nothing stands out as being a bad fit there either. And an autoregressive model also looks pretty good. So they all are capturing this kind of like bimodal distribution. None of the, which I think is the infected and uninfected animals, but none of the models stand out as being a bad fit. So we can't really use this we can't use this graphical check. At least I can't tell that much of a difference there. It doesn't, it's not different enough to say what one's better. So that was the posterior predictive check. Well, let's compare the models. I often use, I think Zach was talking about this yesterday in the office hours, the leave one out cross-validation to compare models, but that does not work very well with these kind of like autocorrelation models. So I won't get into the details of it, but what we're going to do is use cross-validation, k-fold cross-validation to compare the 3 models and get basically a cross-validated information criterion to see which model is the best fit for the data. And we're not going to run this code in here because it takes a lot of computation time. And the reason for that is if you do what cross-validation, k-fold cross-validation means is, well, let's say you do 10-fold cross-validation. That means 10 times you're going to take 10% of the data or 1/10 of the data hold it aside, fit the model to the other 90% of the data, then predict that 10% that you held out. Repeat that for the other 10% of the data until you've done it for all the data 10 times. And what you end up with is a measure of how well the model fits data that wasn't used to actually fit the model, how well it does on new data. And so we have to do this k-fold cross-validation, grouping it by animal. So we'll remove the data for entire cows at once, and then basically split the cows up into 5 groups. Take away 1/5 of the cows and fit the model to the other 80% basically, and then and do that, basically fit each model 5 times. Yeah, can we split data 70-30 for training and validation? Yes. So that's, yeah, basically we're doing a training and validation split 5 times in an 80-20 split each time until all the data is done. Yes, 70-30 would also be a legitimate way to do it. You can change up the arguments of the cross-validation function to do any split you want. And you can, yes, setting a random seed is good for that. Is there a general standard for the training testing split ratios? I think 5 to 10 folds, so like 20% to 10% split is kind of the sweet spot when it comes to cross-validation, because to any more than that, you have to fit the model way too many times and it would take forever. Any less than that, you're kind of like harming yourself by not, if you fit the model to only like 2/3 of the data and then predicted the other 1/3, you're kind of like reducing the amount that's using to fit a little bit too much. So I like to use 5 or 10. Well, I won't, as I said, I'm not going to run this code, but I put it in the worksheet. But basically what you get from the model comparison from k-fold is a sort of comparison statistic for each model. And the one at the top is the best. It's called ELPD. It's kind of like if you know AIC score, you can think of it in a similar way where like you're getting a statistic of how well the model fits the data, accounting for overly complex models are penalized. So the unstructured covariance has a lot of parameters. So it would even though it can fit the data more closely, it's not going to do as well on new data because it's overfit to the data we have. Now the AR1 model performs the best. The unstructured is worse on this, is expected log posterior density essentially, and it's 40 units worse. And the this compound symmetry model is terrible compared to the AR1 model. It's much worse. So James is asking if AIC and BIC can be used. Those are used for the classical statistical models. They don't have as good of properties with the Bayesian models. So we use we use different information criteria for the Bayesian models than we do for classical statistical models, but they have a similar interpretation. They're both based on the likelihood, essentially, with a penalty for how many parameters the model has. Yes, so we say, okay, our model comparison has showed us, yes, no, it's fine to use AIC for your generalized linear models in classical statistics. Yes, definitely is great. No problem there. Yes. Yes, it's just that different branches of statistics have different criteria that are used to compare models. So yes, we've kind of determined that the AR1 model performs best and the compound symmetry performs very poorly. And the reason maybe that AR1 performs best is that the weight gain of an animal over time is like an autoregressive process, meaning the weight at time t depends on the weight last time. So it makes a lot of sense if AR1 model would do best, because we know from our knowledge of biology, basically, that it's appropriate model, not just because of how well it does on the data. We actually have, we actually have biological knowledge that this may be a good model. But like I said a minute ago, compound symmetry, if something is being subject to random environmental fluctuations, compound symmetry might be better because there's not as much of a time dependence of the correlation. Things are just more random. So yeah, can we use root mean squared error? Yes, you could use that as well, as long as you use a cross-validated root mean squared error, because if you don't do cross-validation or the root mean squared error on the test data, root mean squared error is going to get better and better for very complex models, and it's not going to penalize you for having too complex of a model. So yes, as long as you use it on the test data or cross-validated, then it's fine. Yeah, definitely. If prediction is your goal, go for that. But here we're not caring as much about prediction. We're just trying to do inference on the treatment. So root mean squared error is not as important for us as it would be if you're doing like a predictive model. Thanks for the question. But I also want to mention another point is I kept telling you how terrible unstructured covariance model would be because it has hundreds of parameters. And that would be the case, especially in classical statistics. But because we use the Bayesian prior to shrink the parameters, actually Bayesian can do okay with even very complex models like unstructured covariance and not overfit the data too much. So actually, unstructured covariance model it was not the worst one. It was kind of like second best. So that's just illustrates that Bayesian approach can actually do reasonably well with very complex models. But even so, the AR1 model is just a lot better because it only has one parameter and compared to 253 and in this case. So that's just a big advantage. If it can fit the data reasonably well, then we can go with that. It's much more interpretable as well. You could say what that one parameter is instead of having to throw 250 parameters to tell people what's going on. Obviously, simpler models are more interpretable, so that's another reason to go for AR1 in this case. Yeah, I think now would be a good time, I would say, to take a 10-minute break because we've gone through this model, and the next little bit is doing what we've done in the past, making model predictions of the means and then showing figures and tables and stuff like that. But let's let me take any questions real quick, and then we'll take a 10-minute break. Does anyone have any questions? We have scaled the response with standard deviation of 1. Wei Chi is asking, why are we still using the prior with normal of mean 0, standard deviation of 5, which is much larger than the range of the response? Yes, I could have made it even smaller, but I was erring on the side of being conservative and using an especially wide prior, wider than it had to be, just to make sure that I wasn't influencing the results to shrink the coefficient estimates too close to 0. Yes. So yeah, I was just erring on the side of caution. You probably would have got a very similar, if not identical answer if you would have used 2 or 1 or something as a standard deviation. I doubt it would change. If you want to play with it, I would highly recommend. That's why you have this code environment. You could change up the priors to anything you want. I'm not going to do it right now because it would take a long time to run the models, but you could change them up and see what happens. My gut instinct is it would not change it much. Yeah, what do you suggest if AR can't work due to a handful of missing days? Yeah, so that's another point. AR1 is really only supposed to be for equally spaced time points. The cow time points are not exactly evenly spaced, but they were close enough that I said like some were 8 days apart, some were 10 days apart and that kind of thing, but they were close enough that I just ignored that for this purpose. There are other covariance structures implemented in BRMS that can deal with some missing values and unevenly spaced time points. There's one called OU Ornstein, Uhlenbeck, that is kind of like AR, but for unevenly spaced time points, which can handle some of the missing values. So definitely take a peek at that one. Yeah, the AR one is just kind of a simple one. There are other ones you could use, Zach. Yeah. What are your thoughts on bootstrapping for missing data? I think, wow, we have a lot of questions. Okay, awesome. The bootstrapping for missing data, I think is fine. Yeah, again, since this data set only had one missing data point, it's not enough to care about. But if you start to get up to like 5, 10% missing data, you do want to think about modeling the missing data. And yeah, that can be done in several ways. You can do simple imputation, just like fill in any missing data points with the mean or something, or there are more complex ways. And I think again, like with anything, it's nice to do a sensitivity analysis, try out different ways. We don't really, I can't get into a full discussion of how to deal with the missing data right now, but I am making notes because I know a lot of people have asked about power analysis in Bayesian context as well as missing values. So these are ideas for me for future training materials. I'll definitely keep that in mind. Okay, so Anna got, it looks like a warning that some of the transitions hit the maximum tree depth limit of 10. So that is, it is a technical issue with the sampler that basically every iteration of sampling from the posterior, it's using this algorithm to determine the optimal, it sort of randomly moves from place to place in the parameter space to sample the distribution. And there's like an algorithm for the optimal way to do that. And the default is it'll only take like 10 steps through the decision tree with each iteration. And so some of the 4,000 samples like reach the maximum and without coming up with an optimal. So it's like maybe a few of the posterior samples aren't perfect, but if everything converged and you see it only happened in 10 out of 4,000 cases, I wouldn't worry about it. But if it's like 1,000 out of 4,000, you could start to say, well, you can actually increase the maximum tree depth limit above 10 if you wanted to, and it would make things go a bit slower, but because it's doing more with each step, but it will get rid of the warning. So yeah, because it's so few number of samples that is affected by that, I would not care about it if I saw that. Yeah.
But it does have to do with the data in the model, not with like computational.
Well, yeah, it is computational with the sampler, but the more complex model trying to fit to data, the more likely you are to run into those computational issues. So it is related to the data. Yeah, I mean, again, since it's so few, you could increase it. It would not change the result in any measurable way, I would say. But if you had a lot, I usually try to like, yeah, my first step is always to like think about the model. Is it too complex? And then if you really want that model, then you start to work with tinkering with the sampler to make it work better. But like, yeah, your first instinct should not be to try to fix the sampler and make it better because the sampler is doing its best. It's just like sometimes you're like trying to make it do too much, for the data you have. Do we need to make sure the data is stationary before applying any AR structure, like remove the trend? Well, we're kind of doing that the trend is in the fixed effects of the model. So like we're doing that. The AR refers to residual variation after the trend is accounted for, and the trend is that we put days as our fixed effect predictor in the model. So that is that positive trend over time. So yes, that's what we're doing. We are modeling the trend over time of all the cows are growing, so their weight is increasing. We've modeled that trend as a fixed effect, and then we are saying, okay, after all of that, because of the fact that cows are not an individual cow, measurements over time are not independent, we're putting this structure on the residual to account for that. So yes, that's basically what we're doing, but we're not doing it in two-step process. It's all within the same model. So thanks for that question. Okay, great. Well, let's just take a break and come back at 10:30 or 9:30 Central to keep working on this. Thanks again for. I'll be right back, and then I can answer more questions during the break if folks have them. Yes, I will. Answer that question in just a minute, Mahesh.
So something I think I understood.
I should have been unmuted for that in case anybody cared about it. But hey, Mahesh, are you there? I can answer your question if you're there now. Otherwise, I'll wait till the break is over. But well, I'll wait till 10:30. Yeah, hey there, Mahesh. I just wanted to address your question about the model unstructured covariance thing. Basically, the reasoning is that model, the unstructured covariance model, is very complex and has a lot of parameters. And the default sampling options of BRMS the model did not converge when I sampled the model with the default sampling options. The default is to do 1,000 warm-up iterations, which is used to tune the sampler, and then 1,000 sampling iterations that we have as our posterior. I increased the number of warm-up iterations to 3,000 before doing 1,000 sampling iterations, which makes gives this tuned the sampler more so then the model converges. And also I initialized by default also BRMS initializes the parameters to random values. You can also specify what it initializes to, or you can initialize all parameters at 0. For the Markov chains will start with all parameters set to 0. That only is during the warm-up time. It won't affect the final result, but for some reason, when I tried it without the initialization 0, it made a lot of errors. And so basically by trial and error, I found out that if I initialized the parameters to 0, the model would sample. So yes, that's kind of like, yeah, all of this in practice should be red flags of this model being a little bit too complex for the data if you have to do stuff like that. But I wanted to just illustrate how those different covariance structures work. So that's why I did that. Yeah. Let's see. So I think I'll get started again. My thing fell asleep, so I think I might have to reset the path to Stan. So I'll copy that and run it again. And it's annoying why that keeps happening on here. But the next thing we're going to do is we've basically fit a bunch of covariance structures, determined one of them is the best, which we probably could have guessed without doing all that because it's most appropriate for the type of data biological system we have, but we tried them all out anyway as a proof of concept. And now we're going to do what we've been doing every other time, which is we've identified the model, made samples from the posterior, and now we're going to use that posterior to make inference about the thing we care about. So all this time autocorrelation stuff is just like a nuisance to get out of the way and make sure we account for so we can actually look at the answer we care about, which is the weight gain rate of cows affected by if they have tuberculosis, and if so, does iron supplementation change that? So we're going to use another function from estimated marginal means, EM means package is called EM trends, estimated marginal trends, because we're actually trying to make inference about the slopes of these lines. Are they different between the treatment combinations? We want to say, are these slopes the weight gain rate? We could also ask if the mean weight is different on particular days, but for this question, let's say we're interested if the slope over time of these lines is different. So let's let me let's see here. Isn't it, switch tabs here. Here we go. My bad. Here, 1 second. Where were we? Okay, so we've compared the models, and now we're going to do inference. And there we go. We're going to look at the slopes if they're different. And EM trends, we're going to do comparisons of iron supplementation within each level of tuberculosis infection. So we kind of were saying, well, we know we're not going to care about comparing infected and non-infected cows. We're going to compare iron supplemented and not iron supplemented cows within each infection group. Because let's say we already know tuberculosis is bad. So we're really, the experimental question of interest is more about the iron effect, right? And so that's what we're going to do. Within each level of infection, we're going to compare iron versus not iron. And we're going to do reverse pairwise because we want to subtract the control from the treatment mean to see if the treatment mean increases the weight gain rate. And I'll note to address a question we had earlier that these slope values are not going to be in kilograms per day anymore, right? Because we have standardized, we scaled the weight variable to be in standard deviation units. So it's actually going to be in standard deviation of weight per day. But I'll show you later how to transform it back to something you can interpret. And so, yeah, reverse pairwise between iron and infect, but we have to add this other argument, var, which is what is the variable, the time variable that we want the slope over. So we want to compare the trends over time, over day, between the iron groups within each infection group. Clear as mud. Okay, so let's do that. We want EM trends, estimated marginal trends, and you see that we're using the autoregressive model to make inference, AR1 model. We want reverse pairwise, so we want the difference with the treatment minus control. We want to compare each level of iron within each, compare iron. So basically comparing the slope of the thick orange and blue line, if they're different, and is the slope of the dotted orange and blue line different? And the time variable that we are comparing is day after start. EMT underscore Diggle is what we called that object. And yes, we can print out the object by typing it into the console. And you can see we have point estimates for the trends, and the slopes are quite similar, right? The no iron and iron within non-infected cattle, it's in units of standard deviation per day, are both around 0.005 with a credible interval it doesn't seem like there's much difference there. The infected cows are both, maybe a little less than the non-infected, 0.004, but there's not really any difference in weight gain rate, I would say, based on iron supplementation. It's quite similar. And if you take the contrast, if you subtract these two numbers, the 0.00535 and 479, if you subtract these two numbers, the difference is very small, close to zero. You can see the credible interval means we have evidence is consistent with a small negative effect and small positive effect. There's not really evidence one way or the other for an effect. The estimate, the credible interval is is on both sides of zero by quite a bit. So and the point estimate is almost extremely small, very close to zero. So we say, well, iron supplementation does not seem to, at least we have a small sample size again with only couple dozen cows. So there's not a lot of evidence for an effect here. It's not letting me switch the tabs anymore. Let's see. And if you want, you could even contrast those contrasts, but I'm not going to do that. That would be like, is the effect of iron on weight gain rate bigger in the infected versus non-infected? But we've already seen they're both close to zero, so I didn't bother with that. And we can also get our Bayesian p-value analogs by calling describe posterior on those contrasts. I just didn't, I put CI equals null to not print the credible intervals, but you could put one if you wanted to. I'm just going to do the two different p-value analogs, the probability of direction and the p-map value. So we can do that by calling describe underscore posterior. And the object you want to do is the contrasts that are within this trend object. And we want to test with those two different p-value analogs. And if we hit Control Enter, we'll see what we get. Yes, so you can see the median estimate. Yeah, that's the same number here. The minus 0.000562. That's this value. The difference in slopes between iron and not iron for non-infected cows, and the p-map value is very high, indicating there's the ratio of evidence for the null versus zero difference in the slopes versus what we observe is quite high. So we don't want to say that iron supplementation is doing much here. Yes, and I have also included some stuff in the lesson text, which might be helpful to you, which I'll go over briefly, of how you would write this up in a manuscript. So yeah, basically, I would say in this case, we did all that stuff with model comparison, comparing the different covariance structures. I would usually just stick all of that in the methods and not put it in the results, because it's more of a technical aspect of the stats. It's not really a interesting science result that you're presenting, but it's kind of a technical aspect of the model fitting. So I would usually, in my opinion, it belongs in the methods where people can just skip over it and not care, and not in the results. So only if people are really interested in the modeling aspect of it would they look at how you like determine the optimal covariance structure. Other people might do it a different way, you know, but like if you were giving a talk on this, you probably wouldn't like go into all the model comparisons of covariance structures and stuff. You're just going to want to give people the results with the statistical model you determined was good enough and stick with it. So like it's more of a detail in the methods to me. That's my opinion. So I would throw that stuff in the methods. So that's what I do here. You put in, you know, describe the model and talk about the priors, talk about how you sampled the model. And then, yeah, and then you would say, okay, we determined the ELPD value was best for the autoregressive model after doing the k-fold cross-validation. I guess I should have said 5-fold cross-validation because that's what we use. But yeah, and then say, okay, so in the results, we're going to talk about the autoregressive model, and you can ignore the other ones because they were not a good fit to the data. So that's how I would usually do it. And in the results, basically now all of that complicated covariance, whatnot, is just like something that was in the methods, and the results are your basic simple result of here are the slopes. And you can see I've transformed the values back to units of kilograms per day. So the difference in weight gain rate was, you know, whatever, 46 grams per day, which isn't much in the size of a cow. So so we can say that's like not a big difference of iron supplementation. And I give the credible intervals and the p-map values as well. And the figure, again, I don't want to get into the code of it right now, but what I like to show, as I said yesterday, is it's cool to show model predictions and raw data on the same figure, although this figure does get a little bit busy, but I tried to do that here. And I basically had to estimate the model posterior predictions for a bunch of different time points by treatment combinations, and then plot that with their credible intervals on top of the data. And within there, yeah, so I had to back transform the scaled weight value back to kilogram units by multiplying by the standard deviation again and adding the mean. So that's undoing that Z transformation we did. And yes, I had to also say in the plot, I did not include the autocorrelation within cows in the model predictions. We just want the overall average prediction for a treatment combination, not accounting for the variation within each cow, at least just for the figure. We could plot the model predictions for individual cows if we wanted to, but typically I wouldn't do that in the paper. So let me see if I can pull up the code for that and then show it on in R real quick. I have it in the lesson text here. Yeah, well, actually, this is what the figure looks like. I'll just show it on the screen. You could copy and paste and run this code if you wanted to. But basically, I've put the raw data as thin lines in the background and then these are the modeled trends. And you can see I've put a shaded area for the 95% credible interval around the predictions, and they're quite overlapping. So that helps also illustrate there's not a big difference here. And yeah, the slopes aren't identical, but the difference isn't big enough to have statistical evidence for a difference. And yeah, I think I also want to mention there's sort of two ways I might improve this. One is the lines aren't quite linear, right? There's sort of this flattening trend over time. You could account for that. And also there's maybe a relationship between the mean and the variance a little bit as well. So those are both things that you could maybe try to improve. But since we already don't really see a difference with this simpler model, adding those complications is going to just complicate things without adding any new knowledge. So I don't think it would necessarily be worth it. And as for tables, yeah, once again, I transformed back from the standard deviation units back to the kilograms per day units by multiplying the slopes back by the standard deviation again. And so then you can get the weight gain rate in kilograms per day for each of the 4 treatment groups and its credible interval. And I've thrown in 66 and 95% credible interval, which I like to do because that's roughly equivalent to 1 and 2 standard deviations in normal distribution. So yeah, I mean, that's kind of why I think 95 is used in the first place, is because it's 2 standard deviations from the mean. But you can also, yeah, 66 is about 1 standard deviation if it's roughly normal. So I present both those. Yeah, and so yes, you can see they're all in the same ballpark there. And I see a question from Mahesh. Is it possible to show a scatter plot, which is one of the performance? Can you clarify what you mean there? A scatter plot of what?
Predicted versus RZ of the EXI plot.
I'm sorry, I didn't hear that. Sorry, observe versus predicted plot. Yes, you could, and that would, yes, that's definitely, something you could show, right? Because this sort of indirectly gets at that, because we have the observations and the predictions on the same plot, but you could also plot it as observed versus predicted. Yeah, you see that more in like predictive modeling context instead of sort of inferential statistics, but there's no reason why you couldn't do that. And yeah, I think that would also be informative. Yep. Okay, so let's go ahead and get to the next part of this. So that was pretty cool. Doing the residual covariance is neat and very useful. But I think this is an even more powerful way to account for variation in space and time that maybe can give you some interesting inference also, which is to do spatial additive model. So let's talk about that. This will be the last I know we've been, at this for a day and a half now. This is the last case study that we're going to do, but we have, 2 hours to devote to it. I don't know how long this will take. Probably about another hour. But we'll do another half hour or so. We'll take a short break and then finish things up. Yeah. So I mentioned this earlier, but there's two ways to deal with the variation in space and time. One is to put it in the residuals, which we've shown how to do with time. The other is to actually put it in the model itself as a effect. And while time correlation in the cow example was kind of a nuisance, the space one, we could actually make inference about patterns over space and time if we put it explicitly in the model. Now, you could say, okay, well, why don't we just like throw in space or time as a fixed effect, like put X coordinate and Y coordinate as a fixed effect. Yeah, you could, and that would actually work decently in many cases if you have, let's say, a very strong gradient of environmental variation going from north to south on the y-axis or going from east to west on the x-axis. If you had that, then throwing in just X and Y coordinate of your data points as a predictor is actually going to account for that pretty well. And that would actually do decent. But in many cases, especially with any kind of geospatial data, you're not going to have those linear trends like that. The gradient of spatial variation is not just going to be in one direction in X or Y. So you can't just put a single linear covariate for space or time in your model. It often will not work well. So what do we do instead? We're going to use a generalized additive mixed model approach. That means we're going to model the response variable, whatever our Y variable is in the model. In addition to whatever other fixed and random effects we have in there, we're also going to put in a function of the technical language is some combination of unknown smooth functions of the covariates. So that's called a spline or a smoother. You can think of it as a wiggly line. We can account for any by adding up different polynomials. We could make any wiggly line we want to fit any trend in the data in space or time. And you can use there are a lot of different type of functions to do this. We're not going to get into the details of that very much today. This is just going to scratch the surface of what you can do. But the other good thing about these generalized additive models is obviously if you made a line wiggly enough, you could perfectly fit any data trend, right? You just make the line go through every data point in the model. That would be bad because it would overfit. These GAMs have a built-in way to penalize overcomplicated models that are overfit. And so I'll show you an example before we actually do it hands-on. This is just a very simple spline, generalized additive, not a mixed model. This is data that shows you basically the acceleration of a crash dummy's head that was in a motorcycle crash. It makes you not want to ride motorcycles, basically, if you think about it. But like here, the acceleration, it rapidly decelerates when it hits the wall or whatever, then snaps back and then stops again. Yeah, not bad news for the dummy, right? So basically, obviously, there's not a linear relationship here. It kind of is a funny wiggly line. We can fit a GAM, a spline model, which is like a combination of polynomials to try to fit the trend in the data. Obviously, if you just fit a single linear regression through this, it'd just be a flat line. That would be a terrible fit to the data. You have to specify a parameter called K, which is called the dimension, the basis dimension of the spline, which basically determines how many local functions are added together to produce your overall spline. The higher that number is, the closer fit you can get to the data. So in this particular example, if you have K equals 5, it's starting to approximate the shape of that data a bit. It curves down and up again. It sort of has like 5 segments to it in a way that are smoothed out, but it's not a great fit to the data yet. Obviously, we have capturing what's going on. If you have k equals 15 in this case, okay, like that's an extremely good fit to the data. It is tracking what's going on, the up, the down and up. And now look at this. If you have k equals 75, to me that looks identical to the k equals 15. It only got so wiggly, and that's because of the built-in penalty that is keeping it from overfitting the data. It is finding, if you set k too low, it's just not complex enough to fit the data well. But if you set k too high, it's not a problem because it will penalize the overly complicated model. The only reason to not set k too high is computationally it's harder to fit that model. So the GAM will somehow built in, it penalizes the overfitting. I won't get into the mathematical details of that, partly because I don't know them that well myself, but yeah, you basically, just in practical terms, you can say, well, we want to fit this data as close as we can. So just make sure that your k is high enough to capture the trends you want to in the data. Yes, and as I said, I'm only getting a little into this, and I have some other things you can read in the further reading section at the bottom of the text version of the lesson if you're curious about it some more. Does anyone have any questions before we keep going on? Okay, but of course, please interrupt or put it in the chat at any time. Yes, GAM is good for fitting, but very uncertain for predicting outside the X range. Yes, that's 100%. Yes, it is. You would not want to use this to make prediction about what happens after this time, because it's only fitting, the data that's here. Yes, that's true. It is not going to be able to predict new data very well. So this is like, we're using this for inference. Thank you for that comment. Okay, so let's get introduced to our last example data. We're looking at barley in Scotland. So if you like Scotch, this is a good data set for you. Again, it's from the AgriDat package, and they did a field trial of barley in Scotland. And yes, variogram. We're going to talk about that in just a minute. Yes, this is a field trial, an agronomic field trial, where they have a bunch of genotypes and planted them in plots in a field. And not only did they plant 70 different genotypes, there's also 2 different fungicides that they wanted to see if they could be used to improve the yield of the barley. So we have full factorial, 70 genotypes by 2 treatments, basically 140 plots in every block. And this is a split plot, randomized, complete block design. So basically they're within each block, which has 140 plots, there's sort of, the plots are split in half, and half of them, which has all the genotypes represented, got fungicide and half did not. And there's 4 blocks. I'll show you what that looks like with some maps, if that doesn't make sense to you from the verbal description. And so, yeah, this is also in the AgriDat package. It's called Durban split plot is the name of the data set. And the field they had was very long and narrow for the study. So the plots are all next to each other in a long line. And there's 10, the X and Y coordinates, for whatever reason, in the data set are called bed and row. So the beds are like the individual plots that are organized in rows. And so let's take a look at the keeps going to sleep. Let's take a look at the field map by making some plots of the data. Once it loads up. Okay, so we'll load the data using the data function. And then we'll yes, we're going to plot the every time we're going to make maps of this study area with bed and row as the X and Y coordinates. We're going to first show where the different blocks are by coloring in the tiles by block. We're going to show where the different fungicide treatments are by coloring it in by the fung. That's the name of the column with fungicide in it. We're also going to show where the different genotypes are by filling it in by genotype. We're going to make a few different maps. We're going to do bed, row, and block. So you can see there's 4 blocks, each of which has all the treatment combinations in it. They're in a long skinny line because that's how the field was shaped that they did the study in. Where are the fungicide treatments? We can look at that by looking at the fung column for each plot. They're called the main plots. So you can see each block, half of it, this is like how they're physically laid out in space. Half the block got fungicide and half did not. And it's sort of like randomized within each block which side got fungicide and which did not, which is the proper way to do it, to design an experiment. And let's also look at genotype. Where are the genotypes? So you can see where the subplots are. You can see they're just there's a lot of different genotypes that are in tiny little plots within those main plots. Call them subplots. And lastly, I would like to show you the yield response variable. So let's fill in by yield as well. And we specify an orange color palette. So the darker the color, the higher the yield in this map. Okay, so we can see, you can see there's like a treatment effect, right? Because you can like sort of eyeball where the fungicide, like this block, got one fungicide treatment for this main plot. You can see it's just looks different. You can see the line where the yield like drops off in between. You can kind of vaguely see that there's some difference between the blocks that are getting different fungicide. But you can also see that there's spatial variation in the yield that is not an effective block. Like here, look at this top middle. There's like a long strip where the yield is low for whatever reason. Who knows why? And like here, down here, the yield's real low. All these are right next to each other, have low yield, right? So there's like spatial correlation in the yield that's not accounted for by genotype or by treatment, because they're just near each other. So like maybe the patch of soil has worse properties there, and here the yield's just extremely high, higher than any of the other ones in the same treatment. Why is that? You can't account for that just by treatment, or even the block effect is going to take care of some of that, but it's not going to take care of all of that, because some of the blocks only vary from east to west, and there's also yield differences from north to south. That's not going to be accounted for by block. So we would expect there to be spatial autocorrelation in the residuals. So yes, so as I said, we can't, yes, the block random effect is actually going to do a decent job of accounting for some of that spatial variation, but each block has 140 plots in it. There's variation spatially within those blocks as well. So having a block random effect is not going to take that into account because there's so many, we have such large blocks that they're heterogeneous within the block. So once you get to like studies with hundreds of genotypes, the blocks get so big that that it's heterogeneous. Are there units for each variable? Maybe we should shut the door if they're doing like, do you mind? Thanks. If they're vacuuming out there. Let me check the documentation to see if there's units on the yields. If you look up there's only one the coordinates are not in units. Those are just numerical IDs for like row 1, 2, 3, going up to 10. There's no units on that. I don't know how large the plots are in meters or anything, but we're just going to concern ourselves with whether two plots are adjacent in space or how far apart they are by number of plots. We're not going to worry about actually the dimensions of the plots. And the yield, yeah, so you can see the yield is in tons per hectare. So that's nice to know that they actually provided that information here. Yep. Let's see. Going back to the slides. And I also want to, you could also, the human eye is good at picking out patterns when there isn't any. So just to, as by way of demonstration that there is kind of a spatial pattern that isn't accounted for by treatment and block, I just wrote this code to randomly shuffle the yields within each block and within each main plot, and then plot it again. And if it looks more random than the data, or then actually plotting where they are in space, then it's like, well, there's probably a spatial pattern in the data. So yeah, this random seed is just to make sure you get the same result every time. And then I use this sample function to randomly shuffle up the locations of the plots within each block by fungicide group. So within each main plot. This is just sort of for proof of concept. Yes, so we're just going to sample by yield, and then I made this new column called, we have to group underscore by block and fungicide. We're going to make a new column called yield shuffled, which is sample yield, which means randomly shuffle the yield values in space. And then we're going to make a new plot with the fill color being yield shuffled. I'll run all that code. Yeah, so here's the yield shuffled. You can still see the difference in the blocks, but we don't see the sort of patches of low and high yield at the top and bottom of the plot anymore because we've randomly shuffled them. So we've got, if you go back, we can look at them both one after the other. Yeah, here's the one that's not shuffled, and here's the one that's shuffled. You can, yeah, we've gotten rid of some of the spatial patterning by randomly moving things around within each main plot. Just as a part, a way to illustrate there's something going on there. Okay, so back to the slides. Now we're going to fit a linear mixed model to these data without accounting for the spatial autocorrelation yet, to compare it later on with one where we have an additive model to model the spatial trend. Yes, we're going to use genotype, fungicide, and the genotype fungicide interaction as the fixed effects, because that's the way the experiment was designed. And I also, this is just another way to scale the, you don't have to pre-standardize the variable. You could actually scale the response variable within the model itself by putting scale around it in within the model. You can actually, you don't have to create a new column. You can actually scale it within the model. And again, we do that for numerical reasons, but also because once we know that y is in standard deviation units, it will help us keep we can use a prior, we don't have to think about what units the data are in before is it in kilograms per hectare? Is it in tons per hectare? Doesn't matter. We can use a normal prior with a small single digit number for standard deviation, showing that we are encompassing fairly large negative and positive effect sizes in what we have a high probability for. Yes, so this, I guess in this case, instead of using the interaction shorthand of asterisk, I've written out the interaction, the main effect, genotype and fungicide, and genotype colon fungicide, which means the two-way interaction term between genotype and fungicide. So we're saying every genotype has its own mean, every fungicide has its own mean in the model, and we're also estimating the mean for every combination of genotype and fungicide, every interaction between them. So we're going to run fit this model. So I've left a lot of blanks here. We're going to scale the yield variable. And I didn't mention the random effects yet. I will in just a second. Yes, thank you for the, yes, we could have used a shorthand of just putting genotype asterisk fungicide, which is a shorthand for all main effects plus two-way interactions. So we could, yeah, you could write genotype plus fungicide plus genotype colon fungicide, which is the same as writing genotype asterisk fungicide. And the random effects, we need to do block as a random effect. So each of the 4 blocks gets its own intercept, and fungicide by block. That means each half of the split plots, the main plots, get their own random intercept as well. This is sort of the standard way of writing the random effects of a split plot study. Yep, the block gets a random intercept as well as the main plot. That is going to be how we'll write this original model. So again, this is just a regular linear mixed model. It is not accounting for space explicitly in any way. We'll use 0 and 3 as the parameters for the prior distribution on the fixed effect. Oh, and because it went to sleep, it reset the command stand path, so I'll have to run that again. Go back and run that one again. Okay, we'll run that model. Okay, and the thing you want to do now is say, okay, if our model is capturing everything it needs to, the residuals should be random. We shouldn't have any pattern in the residuals. If there's a pattern in the residuals, that means you left something out of your model that should be in there, because residuals are supposed to be random variation in individual data points that's left over. So if we have a pattern, that means there's something going on with the yield that our model missed out on. Our fixed and random effects did not capture it. So we don't want to see any pattern in the residuals. No trend up or down, no variation in space that's, in some consistent way. It just should be random. And we can I made this code here to plot the residuals. There's a function called residuals, which will pull out the mean, because in a Bayesian model, you don't just have one residual for each data point, you have one for every posterior sample. But we're just going to take the mean across all the posterior samples of the residuals so we can make a plot. We just want to do this for plotting purposes. So we're going to add a column to our original data with the model residuals, and then we're going to make a map of that. That's what this code is doing. Yes, we're going to use the residuals function first off to get the residuals of the model. We'll run that. It takes a second to run. And if you look at it, we have 560 rows in that, which is the same as the amount of data points we have in our model, because we get one residual for every data point. Then we're going to use the mutate function to add a new column to the original data, which is going to be column 1 of this residual matrix, which is the mean. So we put comma 1 to get, we're going to take column 1 of the of this residual output and stick it onto our original data. And we're going to call that new column resid no spatial, because it's the residuals of the model that doesn't have a spatial term. Then we're going to make a plot. Resid no spatial is going to be the name of the column that's going to color in the heat map that we're about to draw. What does it look like? Well, to me, there's still kind of a bit of a spatial pattern in these residuals. You can still see, you remember how in the data there was like low yield here. Well, there's low residuals, negative residuals in the area where the yield was low up there, because the yield, the treatment doesn't explain it, the genotype doesn't explain it, the block doesn't explain it. It's just for whatever reason, the yield in this area is low. All the plots in that area have low yield. So there's like a spatial pattern there. The model missed out on that. None of the fixed and random effects we have in there could deal with that. Same with like this area maybe is a bit higher positive residuals. The model is underestimating the yield, so there's positive residuals. Here the model is overestimating the yield. That's why there's negative residuals. So yeah, you could say, well, this is enough for me to say, is the residuals have a spatial pattern? That could be enough for you. But there's also a formal test statistic that you can calculate to measure the strength of the spatial autocorrelation. So this is like what the variogram would show. If you make a plot of it, you could show that. Now, it's called Moran's I statistic, which is basically it's the correlation between how far apart two data points are in space and how far apart their value is. And it's the inverse distance. So basically, the higher the Moran's I is, the more likely that two close data points are to be correlated. So they to have a similar value. So if Moran's I is very high, there is a spatial autocorrelation in the residuals. And we don't want that. That would be bad. And so Moran's I is a correlation coefficient. Correlation coefficient can be between -1 and 1. 0 is what we want, close to 0, because it means there's no relationship between how far apart 2 points are and how correlated they are. There's no spatial pattern. That's what we want. 1 would be perfect spatial correlation. So you usually don't see negative values. You would usually see positive, but we want to see close to 0. We don't want a high positive number on this. Again, this is not a Bayesian calculation. This is just a statistic we're calculating off the data. And you could do this even if you weren't doing Bayesian statistics. The way you do it is by basically calculating the distance between all pairs of points in your data set by taking the X and Y coordinates of your data and then taking the inverse of that, 1 over the distance. And then we have to set 0 on the diagonal so that any a distance between a point and itself is 0. And then we can use the Moran I function from the R package ape to get the test statistic. So we're going to do that, inverse distance matrix, and then calculate the Moran's I of the residuals of the model. So we're going to use bed is the name of the column for the x-axis. So we're going to fill in bed there. And row is the name of the y-axis. So those are the x, y coordinates of the plots. And we're going to get a distance matrix for them. We'll set the diagonal of that to 0. Okay. And then we're going to use the Moran's I function, Moran.I, capital I. And the first argument of Moran's I is what is the value that we want to see is spatially autocorrelated, which is the residual no spatial column of the of our data. And then we need to give it the inverse distance matrix. So the distance between 2 points of the residuals correlated with how close together those residuals are in space. We can run that line. And so we get a value of 0.04. Basically, even though I'm trying to tell you it's super important to account for this, this is not that high of an autocorrelation. It you know, it even gives you a p-value, so it's a very significantly non-zero autocorrelation. The p-value is basically 0, so so it is higher than we would expect if things were completely random and there was no pattern in the residuals. But in an absolute sense, it's not that high. So maybe in practice, I would say you could get away with not having to worry about the spatial autocorrelation in this case and not bother with the spatial additive model. But I'm trying to teach you how to do spatial additive models, so we're going to do it anyway. I would say, you know, you could, yeah, if it's less than 0.1, you probably are in safe ground ignoring the issue. But this is a good way to diagnose that, though. But we're just gonna forge ahead and do the spatial additive model anyways. And how are we gonna do that? Well, we basically add an extra term to the model formula of the model we had before. And yeah, other than that, the model's gonna have all the same fixed effects, all the same random effects. It's just gonna have an extra spatial smoother term added in. And S is the name of the function that that defines that spatial smoother. It has at least 4 arguments. The first 2 arguments are the X coordinate column and the Y coordinate column. And remember, those are called bed and row in our data. The next argument after that is K. That is the basis dimension of the spline of the smoother. If you remember from the plot I showed you before with the acceleration of the crash dummy, you want to have K be a moderate number that's high enough to fit your data, but not too high to be computationally take too long to run. So I'm using 3 different ones here to kind of, so we can check the model fit of different values of K, 10, 25, and 50. You kind of have to work that out by trial and error in some cases. And the basis of the spline is called GP. This is one, there are many different mathematical equations that can be used to build these splines. A very common one for spatial splines is called Gaussian process. And that is basically, it is a very flexible model that it doesn't make very strong assumptions and can fit essentially any spatial structure in the data very well. But the only reason not to use it is because it is computationally very intensive for big data sets. But our data set here only has 500 or 600 data points, so we're not going to worry about that. So that won't be an issue. So for any small data set, a Gaussian process spatial smoother is a great choice. And I won't get into the details of that too much. And there's many other ways we could fit an additive model. But I don't really think that we all collectively have the time and inclination to get into that today. That would be like a whole semester to talk about. So we'll just say Gaussian process. That's what we're going to use. And again, I got some sampling warnings when I fit these models. The way you would deal with that in practice is by tweaking the priors and adding iterations. But I did not want to get into that for this lesson. So we're just going to ignore those for now. But I'm happy to discuss that more later on. The pedagogical reason of fitting these models is not to make sure they're perfect, is to show how to do a generalized additive model and compare different spline dimensions. So you can see there's 3 here. We have K10, K25, and K50. All the code here is identical, the same exact fixed effects and random effects that we had before, the same prior on the fixed effects, the same number of iterations and all of that. The only difference is this S bed, comma, row, K equals 10, basis equals GP. They're all the same there, except the only difference is K is set to a different value for the three models. That's the only difference between them. We just have three models. So yes, we want, for this first one, you can fill in bed for the X coordinate, row for the Y coordinate, K equals 10, and BS, the basis, is in quotes GP. And the next model is all the same except K equals 25. So fill that in, and then we're also going to do K equals 50. That's it. And then we can just run all that in one go. And again, these are preloaded, so they should run very quickly. And now I mentioned that we want to say which one of these models is the best fit to the data. Is it the model that ignores spatial autocorrelation, or is it one of these additive models? We have three options, which are kind of differentiated by how complex they're allowing the spatial pattern to be. The K equals 10 is not as flexible, but it's a simpler model going all the way up to K equals 50. And we're going to use this leave one out cross-validation information criterion to compare the models. This will give us a similar information criterion statistic that we got for the K-fold cross-validation in the last example. But now, since we are not using residual autocorrelation models, we can take a shortcut and use this leave one out cross-validation. We don't actually have to refit the models many times. It takes a computational shortcut. And then so we're going to add this information criterion to all four models, and then we're going to compare all four of them. And you may get warnings about problematic observations, but it's only for a very small number of data points. So I don't think that's an issue in this case. So we're going to use the add underscore criterion function to add and which criterion are we going to add? We're going to add the LOO, the leave one out criterion, to each of the four models. And then we're going to use this, so we'll run that code. Again, this is preloaded, so normally it would take time to compute those criteria, but it already was computed ahead of time. And then we're gonna use Lu underscore compare to do a model comparison of the four models. What will we find? Okay, well, you can see that the most complex spatial additive model is the best one by far, and basically as the models become less complex spatially, they become a worse fit to the data. And in fact, the model that ignores the spatial autocorrelation is much worse than any of the spline models. So we can say, well, we probably should go with that. And not to mention, and you know, the higher the K, the better fit. We probably could go even higher than 50 if we tried an even higher number. It might be an even better fit to the data. But I think 50, we'll see from looking at some of the diagnostic plots in a minute that this model is just graphically, you'll be able to see it's doing a pretty good job of capturing the spatial trend, and so it's good enough, I think. I'll show you that in a moment. So basically, we've done all the model fitting we're going to do today. The rest of what we're going to do is just kind of like playing with the model we decided was good and showing some of its predictions. And yeah, then we'll be done with our workshop. So we're in the home stretch here. You can see the slides we only have a few slides left. So we plotted the residuals of the model that ignores spatial autocorrelation or spatial trend. let's do the same and extract the residuals of the spatial model, and we can plot them as well with a heat map. And we can also calculate the Moran's I statistic for the residuals of the new model as well, just like we did for the old model that ignored space. So we want to get the residuals function, and we decided that the k equals 50 model was the best model, and so the name of that was Durbin GAM K50. We're going to get the residuals of that model, which we decided was best. Durbin, or well, the information criterion showed us it was best. GAM K50 is the name of it. We're going to add a column to our data with the residuals from that model. And then we're going to plot those residuals. We call it resid underscore spatial is the name of the new column. So yeah, look, here's the one, the plot that's still up here is the residuals of the model that ignored space. What did the residuals look like once we've added the spatial term to the model? It's like, they look nice and random. That's just how residuals should be, random. You know, there's no areas as far as I can see with high numbers. There's no areas with low numbers. It looks like just random. And that's exactly what we want. Residuals should be everything that's left over once everything important is accounted for, and it should be random. So great, that's a success there. And we can also calculate the I statistic for this column. Resid underscore spatial is the name of the column. And we can keep our same inverse distance matrix of the distance between the points. We'll just use that again. And so we're going to do that. Durbin underscore inverse underscore distance. What is our I statistic? So yes, now we have a very, very close to zero number. Yes, it's you know, within 0.01 of 0. And you know, if you like p-values, it's not significant. So now we can say we've dealt, you know, we've showed in several different ways by showing the heat map of the residuals has no trend, and also the test statistic of spatial autocorrelation is quite close to 0. So we're happy that we've accounted for spatial autocorrelation, and we've you know, dealt with that. Now the next step is to say, well, did that even matter? Did this extra work, which if you know, would probably take a lot of time and effort for you if you're a scientist, did it actually make any difference to the inference? Like, because we don't actually care necessarily about space. We just care about the means of genotype and fungicide accounting for space in the process. So let's just take a look if it had any effect. We're going to look at the estimated marginal means of the model that ignored space for every combination of genotype and fungicide. We're going to look at the estimated marginal means of the model that we decided was best because it accounted for space for every combination. Mahesh, are you sure that you ran it on the residuals of the spatial model? Yes. Thanks, Brad, for that comment. Because yeah, the one column was called residual non-spatial and one column was called residual spatial. So make sure that it was the one you get the right, use the right one. So yeah, so I don't think I left any more blanks in the worksheet at this point. Now we're just gonna like run some code and take a look because you're probably all tired of filling in the blanks and stuff. So we're gonna calculate the estimated marginal means for each model, the one that has spatial trend and one that does not. And then we're gonna, I wrote some code to combine all those into one data frame for plotting, and then I'm gonna make a plot of them. So let's take a look at what does it show. Well, it's like, well, that honestly is pretty darn similar. You know, did it really have that much consequence for inference? Not that much. I mean, I guess the one thing you could say about it is, so yeah, the orange orange points are the predictions from the model that did not account for the spatial trend, and the blue dots are the predictions for the same treatment combinations for the model that did account for the spatial trend. I put them next to each other so you could see if it moved at all. And so the one that you could say is that for this fungicide 2, maybe the non-spatial, the orange points are always higher than the blue. So maybe we were overestimating the yield benefit of fungicide 2 a little bit when we were ignoring the spatial trend. You know, you might say that, but to be honest, it's not a huge difference. But you know, you can sleep better at night knowing that you properly accounted for any possible trend in spatial autocorrelation that might have been there. So we at least, even if, and you know, but maybe this difference is biologically significant. You know, I don't really know. So that there is at least some systematic difference between the models, even if it's not a large in absolute sense. So that's yeah, that's that basically. We also want to just go and I thought maybe it would be nice to actually plot what is this. We've talked about this spatial additive term. What does it actually look like? Well, I wrote some code to make predictions of the fitted value of the model accounting for space and averaged that over all the treatment combinations and posterior draws so that we can make a heat map so you can actually see what does this generalized additive mixed model look like? What does the spatial smoothing term look like when we plot its predictions on a heat map? And so that's what this code is doing. Again, I won't get into exactly how I did that, but I just want you to see what it looks like. And so, yeah, once this runs, you'll be able to see what the spatial smoother is actually doing. And yeah, I simplified this to only take 10 draws from the posterior and just average them. I didn't do it over the entire thousands of samples because that would not be necessary just for this mapping purposes. Yeah, so this is what the spatial additive term looks like if you actually plot it. You can see it's kind of smoothed out compared to what the data look like, but you can see it's got a negative value up here in the north center, which is where we saw that low yield area, and it's got high positive value down here where we saw a cluster of high yielding areas. So it's, yeah, this is kind of like after accounting for the spatial, or for the treatments and the block effects, this is what the model is fitting for the extra spatial effect. And the wiggly lines in 2 dimensions is how we can get this sort of patches of high and low over space. So that's what the spatial additive model is actually estimating for us, which is kind of cool to actually look at. Are there any questions? We have, yeah, I think we will be done in 10 or 15 minutes, and then can break for, or take more questions and break for lunch. But I just wanted to pause here before we do the last couple things and take any questions. Okay, I will now do what I've been trying to do every time, which is show you ways in which you could present the results in a manuscript if that's what you wanted to do. And once again, the ever useful EM means package is going to help us out with that. Let's say you wanted to get the model predictions. Again, these are only the fixed effect predictions. We're averaging over everything else. We're averaging over the random effects, and we're averaging over the spatial effects, just to care about the difference in the means between genotype and fungicide. Let's say we wanted to know within each genotype, what is the pairwise difference of yield by fungicide? Like maybe some genotypes do better with fungicide 1 and some do better with fungicide 2. We can ask that question by looking at fungicide contrast within each genotype. We could also get an overall contrast for fungicide by just doing pairwise by fungicide, which will average over all the genotypes. Once again, this is giving us in standard deviation units still, because that's what we fit the model as. Yes, so I'll give you a couple more blanks to fill in. So we want fungicide by genotype, or we could do just fungicide contrast. Estimated marginal means overall. We'll take a look at that one first. And it says, note, results may be misleading due to involvement in interactions. That's because we're averaging over all the genotype effects to get an overall fungicide effect. So if there's a strong interaction, that will not be a meaningful value, but let's look at it anyway. You can see that there's the yield of fungicide 1 in standard deviation units is this value, and fungicide 2 is that value, and here's the difference between them. So on average across all the genotypes, accounting for any experimental blocks and accounting for space, fungicide 1 has a higher yield mean than fungicide 2, and we have decent evidence for that based on the credible interval having all positive numbers there. And we can look at it by genotype as well, but you get a very a lot of numbers there, because we'll show them anyway, because there's 70 genotypes. But yeah, you can see it gives you the contrast for every single genotype. So like for some genotypes, there's a large difference, a large effect of fungicide 1, and some they're small. It seems like for most of them it's a positive. So most genotypes, looks like, if not all of them, do better under fungicide 1. So that's the kind of thing that you could, and some have more evidence for that than others, but that's the kind of thing you could do with this model. And lastly, again, what would we write in the methods here? I didn't put results because I think you've had enough of that for today, but this is how I would describe the methods here. Again, you'd want to talk about the model. And once again, since the comparison of the different models, the model without spatial variation, spatial additive term, and the different spline basis dimensions that we compared, because that is more of a technical model fitting thing and not really part of the results, I would just stick it in the methods. Say this is the delta of our information criterion compared to the other ones, and so I would just put that in the methods, and then in the results only talk about the model that we decided was superior. I guess in the methods you could also mention the Moran's I calculation as well if you wanted to. I didn't write that here, but that would also be the place to do that. And yeah, and then this is what I would use for a manuscript quality table. If you wanted to look at fungicide predictions averaged over genotypes with different credible intervals on it. And once again, I had to back transform it by multiplying back the standard deviation and adding back the mean, and I've got the mean for fungicide 1, fungicide 2, and the difference between them. And I won't run that code. I'll just show you in the lesson text. What does that look like? Yeah, so this is the kind of thing you might show. So I've transformed it back into tons per hectare, where previously we got it in standard deviation units. Here's the posterior median estimate for fungicide 1 versus fungicide 2, and the difference between them with different credible intervals. And again, you could put Bayesian style p-value on that if you really wanted to, although this is really pretty much adequate, I think, to present. Okay. just some wrap up stuff here, and then I'll take any last questions that people have. Yeah, let's all cheer ourselves for making it through 3, or some of you 2 lessons of the Bayesian crash course. And what did we learn today to top off all the stuff we've learned? Thank you. All the stuff we've learned in the past lessons, we've looked at how to deal with relationships in space and time in 2 different ways, by putting it in the residuals or by putting it in a spatial additive or an additive model. And then we've used those models to make predictions and inferences. So yeah, I think you're starting to get the hang of this Bayes thing. So that's awesome. I'm glad to be able to go on this journey with you all. And once again, I just wanted to finish by saying the text version of the lesson has exercises if you want to do some homework on this stuff. I have some links to books, tutorials, blogs that I think are good, any type of resources like that. And of course, if you want to work on this stuff with your own data, you are always welcome to schedule a consultation with me and we can talk about it. And again, this is optional, but if I would appreciate it if you could go to the course page, scroll down to the very bottom, and there's the feedback form, MS form link that you could fill out. Yeah, so that is all I have for you, and so I would be glad to take any questions that people have. Oh yeah, and I will after the questions, I'm gonna take a break, and then let's say at 1 o'clock, 1 o'clock Eastern or noon Central, I will get back on this meeting to do any other Q&A for folks. So yeah, at 1 o'clock, I will do that. Yesterday, you discussed using the logit link function. When using another software, a stat specialist said it would be best for me to use elastic net with my data because it would better represent the lower positive values. Yes, well, elastic net is not, you could use a generalized linear model framework with a logit link function and also use elastic net. Elastic net is like a machine learning type of thing, which adds a penalization of the regression to keep the parameters from overfitting the data. So you could actually use both. Yes, I think elastic net is great. That is an excellent tool for prediction, but it's not an either or situation, because if you have binomial data, you can use elastic net and use a logit link function as well. So I'm happy to talk more about that with you, Cameron, if you want. But yeah, I think elastic net is great. It kind of can be used with, it doesn't have to be used in a Bayesian context. It could be done without using a Bayesian estimation. Oh, did I link to the wrong lesson answer sheet on lesson 3? Let me check that real quick. Yes, okay, yeah, it looks like I linked it to lesson 2 answers. If you just change the 2 in that URL to a 3, it will work, but I will update that on the website. So thank you so much for pointing that out, Amanda, I appreciate it. Yeah, just change, it should, yeah, it's like underscore lesson 2 underscore answers. If you change it to 3, it should, I did post that answer sheet on the site. I just must have put the wrong link in the document. So thanks. Is there any reason we would do a non-Bayesian mixed model? Yeah, so yeah, there's pros and cons to everything. And I would say I am not philosophical. I use the non-Bayesian every day. Like I use all these things every day in my job. I don't have any like axe to grind with any of the methods, right? I just use the ones that give me the answer the best. So, you know, priors is a can of worms, and people, you have to, if you don't want to care about priors or figure out which ones are appropriate, you don't have to worry about them in a non-Bayesian context. So if you don't think they're going to influence the result anyway, then go ahead and use non-Bayesian. And also, you know, yes, people should be open to all methods, but Bayesian is still unfamiliar. So if you like are trying to, if some people won't accept that, you might want to like avoid it because it might make some people's, you know, alarm bells go off or whatever. So you could avoid it for that reason. And yeah, computationally, I think we said this yesterday, with really big data sets, the Bayesian approach starts to become harder to pull off because it's computationally intensive, right? You either have to use Monte Carlo sampling to estimate the parameters, which I mean, I have to run a lot of these models on like the cluster on Scinet because they don't, they take, you know, a day or two to run on my laptop. And so, you know, with big data sets, that starts to become hard. And once you get, yeah, there's other approximate methods that can be used besides Monte Carlo sampling called Laplace approximations. And there's some R packages. INLA is like an R package, INLA, that is used for these approximate Bayesian methods that can work for like bigger data sets, or ones like people use it a lot for spatial autocorrelation models, like what we're doing, because they have a lot of parameters and you can use these approximations. But at real big data sets, even that starts to become tough. So then, yeah, then I would be like, well, let's use like a more machine learning approach rather than a full Bayesian approach once you get to really big data. That's what I would say. Yeah, but great question. Thanks. Thank you. Moran's I is best for analyzing global spatial autocorrelation. How about local pattern? Do we use Ripley's K? I honestly, I don't know the answer to that. Let me, yeah, I don't actually know. So I'm not too versed in like the autocorrelation test statistics. Let me get back to you on that one. Yeah, I'll just have to punt on that one. Is there a way to use GPUs on Scinet? Yeah, I don't know the answer to that one either. So yeah, you'd have to ask the Scinet support. Do you know anything about that?
You
Grant?
definitely can.
Yeah. I mean, I've know people talk at the Scinet meetings about it, so you must be able to, but I don't personally know how to. Yep. Yeah, Scinet definitely has GPU nodes on it, though. I know it does. Yep. Anything else? I'll stop the recording too.